After jamming out with the bros, you might find yourself in need of a tune. For our final project, we decided to make an automatic guitar tuner. When we were on campus, we would have jam sessions all the time with friends in Winthrop JCR at 2 a.m., even during the week we got kicked off. When playing the guitar at our jam sessions, it would often be annoying to have to tune it before we started playing. This process took energy and effort that could instead be spent chatting with friends. And we wanted to automate the process as much as possible. Therefore, we created an automated guitar tuner to help our friends out.
When you normally tune a guitar, you would play a string, and your tuner will tell you if the pitch of that string is flat, sharp, or just right. If your string was flat or sharp, you would turn the peg accordingly to get a closer pitch. You would repeat this process until the tuner tells you that you have just the right pitch for that string. With 6 strings to tune, this process can be a bit tedious, so we closely examined the process of tuning a guitar and saw where we could put servos and circuitry to work.
When figuring out how this would work, we realized that the heart of the system would be a feedback loop. We would input the sound coming from plucking the string into this feedback loop and compare the sound's frequency with the desired frequency of the string. If the two frequencies do not match, we would have a controller determine how many degrees we would need to turn our peg in a specific direction and turn our peg accordingly. Since we decided to have a proportional controller, this value of how much we need to turn our peg would be proportional to our error. We would play the string again and continue the loop until the input and desired frequencies match, hence our string is tuned. Since proportional controllers have a steady-state error, we implemented a tolerance of plus or minus 1 Hz to classify a successfully tuned string.
To measure the frequency of the sound from the string, we would take samples of our input audio signal using a microphone, digitize them, and then take its discrete Fourier transform. Simply put, a Fourier transform takes this very complex audio signal and breaks it down into its component frequencies and corresponding amplitudes. We then take the frequency with the highest amplitude as our measured frequency, since it is the most prevalent. To avoid picking up the sound's overtones, we use a low-pass filter to ensure we are picking up the guitar string's fundamental frequency.
Now that we've explained the theory of how we will tune our string, I'll briefly introduce the mechanical parts that will bring our tuner to life. First, we have laser-cut wood parts assembled together to serve 2 purposes: to pluck the guitar string and to act as a stand for the guitar. To pluck the guitar, we have a timing belt attached to the assembly and glued a bent paper clip to the bottom of our timing belt. A servo turns the timing pulley, which rotates the timing belt and allows the paper clip to strum the string. We also have a simple support in the assembly that lifts up the guitar to a given height because we want to be able to turn the guitar pegs.
To turn the pegs, we created 2 3D printed parts, a servo stand and a peg adapter. For the servo stand, you can move a servo up and down until you lock its position to the height of the peg as determined by the plucker assembly. We need the simple support so that all of the pegs are lifted off the ground and the servo can have a counteractive force to actually turn the peg. The peg adapter is glued to the servo so that the peg can nicely slide into the adapter and the servo can turn the peg.
Now, let's see this bad boy in action. First, we have to press this button to start tuning the string. As you can see, the paper clip moves back and forth and continues to pluck the string until the microphone can detect the sound. The code determines whether or not the measured frequency matches the desired, and the servo then turns accordingly so that we can get to a closer frequency. Simultaneously, our breadboard lights up red if it's sharp, yellow if flat, or green if just right. We have to press the button again to let our circuit know that we are ready to do our next iteration of tuning. We follow the same process until we see a green light.
Throughout the entire process, we ran into many obstacles and frustrations, including the servo interfering with the measurement of frequency, microphone detection of sound, the plucker not plucking the string loud enough, and determining how much to turn the peg, among other problems. We screamed, we cried, we almost gave up. But as you can see, we fixed these problems so that the only part of the system that involves our hands is pressing the button to start an iteration of tuning. Only the servos pluck the guitar string and turn the pegs, creating a truly autonomous guitar tuning system.
Now, we can play a tuned guitar at a bench, outside Left House Best House, to our dog, and by ourselves with a ukulele? Wait, that's another group's project. This is our automatic guitar tuner.
Thanks for watching.